Okay, so this week I'm going to talk through basically the second half of the assembly language lecture. I'm still going to stick with x86 32-bit, 64-bit assembly language. I'm not going to change from that for most of this. Later on in the advanced topics weeks, we might actually start talking about some other options. But in this case, we're going to stick with this because it's what I know best, and it's what probably a lot of you will deal with if you have to do malware analysis in the field. So the previous lecture, I talked about kind of assembly language, reading assembly language, how the language is organized, or I should say how the instruction set is organized. I also talked about, if you remember the control flow graph, those examples that I showed everyone, I talked through how the program itself is broken up into blocks, and then those are translated into assembly. So if you'll remember, the C program will have your kind of if then else statements or the for loop statements, things like that. It'll identify those things as basically block barriers, any place where a branch needs to occur, and it'll break your program up into discrete sequences of instructions called blocks. Once that's done, then it will attack each one of those blocks to translate them from the source code into assembly language. And then finally, that will be translated into machine language, or the binary code, the byte code. So as I said, we're going to focus on the Intel AMD x86 instruction set. So I put those both up there because Intel designed the x86 instruction set initially. The 64-bit version of it that most of you use on all your laptops is a version of it that AMD derived from Intel's original design. So AMD inherited Intel's design initially, and now Intel is inheriting the design that AMD put together in the late 90s, early 2000s. So that's also part of the reason, that history is part of the reason that those two happen to be the only vendors of this instruction set on the market. Early on, AMD actually did a large amount of the chip manufacturing for Intel, and that's the reason why they were able to freely use this, and you didn't see a whole lot of x86 CPU vendors out there initially. So, you know, the two versions, 32 and 64, there's a bit more than just the distinctions I have right here. Between those two, there's actually some architectural changes that I am not planning to get into because, for the most part, they're not necessary for thoroughly understanding them in order to actually do the malware analysis piece. So the instruction set has the following characteristics, and I talked through what some of these things mean earlier. Also, a lot of them I will talk through what they mean in the coming slides. So it has that register memory architecture that we talked about, rather than the load store architecture. That allows you to write instructions that in one operation can operate on data that's located in memory. So it can hide the whole memory fetch and retrieval and stuff like that. You can actually hide that behind the architecture. It has some purpose-specific registers. So if you remember, we talked through how there's kind of this local memory to all the processors that's registers. It has some purpose-specific ones, which means that context is important when using them. So it means that there are some instructions that expect the information to be in certain registers, or that will always put their result in certain registers. Over the course of its lifespan, this architecture has moved away from purpose-specific registers. So that's just worth keeping in mind that sometimes that's the case. It's not always the case, so it's not consistent across the board. It is something that you will run into when you're writing, if you are writing any programs in assembly language, and it's also something that you will run into when you're doing analysis. I will not dwell on it too much in a lot of the examples that we'll work on, but it's a gotcha that's really useful to know up front. In addition to the kind of the architecture with this 32-bit versus 64-bit, it actually allows you to directly access registers for each one of those. You can actually use these, you can use both sets of these on the 64-bit architecture. But basically, you have 8, I'll kind of point to it over here. You have 8 general purpose registers. So you have 8 registers that are local to the processor that you can store data in if you're working with 32-bit code. 64-bit code, they decided long ago that having 8 of those registers is actually not enough, and so 16 would be a better number. Transistor prices came down, that type of thing too. So that was helpful in allowing them to ship processors with more registers. So if you choose to write code in 64-bit mode, you'll actually get twice as much local registers to work with. So kind of high level, the reason the registers exist is that a lot of the variables that you use in the code blocks and everything tend to map directly to registers. And it allows you to have direct real-time access to those. So some of you might be familiar if you've had to buy your own computing hardware with the processor has a certain frequency it runs at, and it may be 3 gigahertz or 3.5 gigahertz or something like that. The memory has another frequency that it runs out, which sometimes might be 800 megahertz. Other times it might be 1.6 gigahertz or something like that, but it doesn't go too far above that. Because it has less frequency, that means that it takes sometimes 2, 4, 6 times longer to read stuff from memory at a minimum. And at a maximum, it can take even longer because of a number of other factors that I'm not going to get into here. But just suffice to say that memory is at least 4 times slower than registers, and oftentimes can be much, much slower, up to 10 or even 100 times slower. So that's one of the benefits of having this. You also have these segment selection selectors, which are another type of register. You will see them used in a lot of code, and they definitely have a specific role in the architecture. They are basically another set of 16-bit registers. I think there's about 4 to 6 of them. You have what's called direct and indirect memory access modes. So this is where you can address memory, so you can refer to data that's in memory, either by giving it a numeric address. So actually say, I want to work with the data that's at offset 1000 in my memory space, or I can give it indirect addressing, which is I would like to work on the data that's located at address 1000 plus the value of some register or something like that. So it's called indirect memory access mode. So not all processors offer this type of feature either. A lot of them do, but not all do. And so that's why it's kind of highlighted as a specific attribute that this one implements. So I had a question to talk about some of my preferred intrusion detection stuff at the end of class. I can jump into a little bit right after this slide, so just hold the question. A lot of the intrusion detection stuff isn't necessarily within the scope of this class. I talked about the memory access mode, so that's basically within those register memory instructions, ways that you can express where data is in memory when you want to deal with it. Variable length instructions, this is another big one that'll be real complicating of, or I should say that will complicate analysis a bit for you, or for everyone, but it's not unique to this architecture, but it's a specific oddity of this architecture. It's variable length instructions, which means that not all instructions are the same length. There's an average length across the board, and a lot of times they'll do instruction counts based upon section size divided by average instruction length, that type of thing, to try and give you the rough instruction count. But there is no real defined length of an instruction, and I'll say that in this instruction set, there's no definition of a maximum length. So they have it set up so that if they want to introduce new instructions, they can basically make them longer if they want. And then finally, in addition to the registers above, it's got some what are called machine registers, which provide insight into hardware. So those of you who've had to do embedded system programming might actually be very familiar with this concept. It's got the instruction pointer itself is a register. The unique thing here is that you cannot actually read the value in it. You cannot read the value of it from your code. You actually have to use tricks in order to get the value out of it. And when we're analyzing malware that attempts to find out what the instruction pointer is, or what the value of it is, you get to learn some of the tricks. And then internal flags. So we'll learn later that all of the instructions, or many of the instructions that perform math especially, will change state flags within the processor. And so the processor may change the outcome of an instruction based upon what the initial flags were, or what the internal flags were coming initially into the instruction. So, so in kind of a nutshell, these 7 features are extremely important in trying to interpret assembly language. So the other thing that I'll add when you're working with it, and this comes into consideration a lot when we are working across multiple tools that are supposed to be doing assembly language analysis, is that, so number one, all the instructions are compact binary structures. So they are set up so that all the fields in an instruction are basically crammed one right next to the other one. They don't typically implement any sort of concept for like data gaps or anything like that. Assembly language itself is a textual representation of binary encoded instructions. So there's usually a one-to-one relationship between lines in assembly language and instructions that are implemented in the binary code. So one of the things that you'll encounter is that there are 2 prevailing methods that are used for writing assembly language, at least for this architecture. I don't know how common this is outside of any chips that Intel makes. But one of them is the first one, and that's the AT&T syntax, or the Unix syntax. So if you are using Linux, and you saw when I was working with OBJDump earlier, Linux actually displays, basically converts it this way. So this is an example of it. The big thing that they're doing here is they list the operation, so move, then they list the source of the operation, or I should say, most of the operations are intended to use some source data and then perform an operation on it, and then write the results of that into a destination. That's how that's generalized instruction concept, and how most of these are built. So the way that AT&T and Unix is supposed to be is, if you look at it in the order of like a infix mathematical operation almost. Basically it's operation, source, and then dest. So the way I always look at it is that Unix basically is operation, source, and then an arrow pointing to the next thing. So Unix is using the right arrow, or the right pointing arrow. And then basically this instruction will take whatever data is in here, and it'll put a copy of it in here. So whatever data is in RAX will be put into RBX. So the other syntax you run into is called Intel or Microsoft syntax, and that's because it's the one that's published in a lot of the Intel reference manuals. I think they're the ones that originally defined the specification for the syntax. And then Microsoft uses it heavily in their assembler. So, another example is that the first one, the AT&T or Unix syntax, that one's going to be common if you are used to writing, or if you're familiar with writing anything in GCC or Eclipse or NetBeans or anything like that. The second syntax basically flips the destination and the source around. And the other thing that's important about the Microsoft syntax is that they typically leave off the data size, and they leave that to be interpreted by reading the instruction or the operand name, the register names. So you'll see that this one's MOVL, and this one's just MOV. That's just something you'll have to watch for. When it gets turned into binary code in the end, both of these things become the same sequence of bytes. So this one, again, Intel Microsoft syntax. If you deal with Visual Studio, you will most likely be seeing that format. AT&T Unix GNU syntax. If you happen to be using Eclipse on Linux or NetBeans on Linux or GCC, you will most likely see the first one. And then if you have very crazy setup where you decided to use the assembler shipped by Intel, then you may end up being in a GCC situation where you are using the syntax still. But chances are, if you're using that setup, you know what you're doing a lot better than I do. So, but the reason I bring this up is because we are going to work with tools that were intended for the Windows use case. And we're also going to be using the tools in this class for analysis that were written with more of the Unix or Linux use case in mind. And the people who wrote those tools are going to use what utilities are available to them to accomplish the end goals. And in some cases, that's the Microsoft disassembler or the Linux disassembler. So Mac will probably be using this one, the Unix, Linux, AT&T one. But don't quote me on that because I have not used Xcode in a very long time with assembly language. So, but the last time that I dealt with Mac, I had to use GDB, which is this, which is Unix, Linux, that's the GNU debugger. And I was presented with the Unix syntax, of course. But that was 13 years ago. So getting to the question about intrusion detection platforms and stuff like that, if you shoot me an email, I can try and send you some information on that. The scope of this class isn't really diving too much into intrusion detection systems. There is another class that is offered in the School of IT, and I believe that they might actually have one at the grad level. I'm not sure. So if you are a grad student, you know Vicki Baker, who's in charge of the cyber program. I'd recommend emailing her. Yeah.
I know that I'm in the IT program, there's a forensics class.
Yep.
Right now, is that what you're referring to?
So there's a forensics class
Yeah.
that teaches you the file system forensics.
Mm-hmm.
There's another one that's called network monitoring or network security monitoring that is also offered through the IT school, and I'd recommend trying to take that as an elective if you want to learn about intrusion detection systems. So beyond that, I would say that a lot of the material that would be covered in maybe Cyber Defense Overview talks a bit about Security Onion, but that's more as like a reference design with a reference design of features, but not necessarily a something that's practical to implement in a business environment or something like that. So hopefully that helps. So I don't, I don't know. I'd recommend looking into the curriculum for network security monitoring, network detections, network intrusion monitoring, stuff like that, or talk to Vicki.
We're working on a Raspberry Pi honeypot right now. So
Yep. Oh, nice.
it's pretty fun.
So this one gets, I'll jump up here. We're going to talk a bit now about the, where is it? Well, yeah, here we go, variable length instructions. So I'll kind of give a jump into that. So x86 instructions, they're a sequence of bytes describing unique atomic CPU operations. So It's a variable width instruction set. There's no fixed size for all instructions. The number of bytes that comprises an instruction varies from one to the other. So here's some great examples. The jump instruction. So this one right here, the first bullet, that one is 2 bytes long. The next one, the move, or in Unix it would be move quad word, it would be move this value. So move that value that's basically 4 ones in a row, or 8 ones in a row, sorry. Move that into RBX. So basically overwrite the content in RBX with this literal value that I've got published up here in hexadecimal format. The next one, this is one of the more complicated ones, so it kind of shows you the expressiveness of this language, and that is to, I'll just read off, add L, and then it is OX12, which is going to be the decimal value 18, and then comma minus OX8, and then parentheses around the register EBP. So what this means is add the 32-bit value 12, or 12 hex, which is 18, to the 32-bit value stored in the memory location. So it means that it wants you first to find out what number is in the EBP register, and that's a 32-bit number. Just as a quick aside, you notice up here I used RBX, RAX, jump into this later too, and then here I use EBP. I cannot explain the reason why they chose these letters, but traditionally the 32-bit versions of a register, when you're trying to use only 32 bits of a register, starts with E. When you're trying to use 64 bits of a register, it starts with R. If they extend the instruction set again, they'll probably come up with a new prefix. So just figured I would do that aside. So that's kind of what's going on here, and that's why I specifically have the 32-bit, explanation, or the 32-bit term in the explanation here. That's where that's coming from. So it said, look at the register EBP. That's a 32-bit register. I want to handle stuff in a 32-bit way. So I'm going to find out what value that register is. And then I'm going to identify that that's a memory location. Then I'm going to subtract the value 8 from that memory location. And then I'm going to get the data at that memory location, which itself is a 32-bit value. I'm going to add 12 hex, or 18, to that value. And then I'm going to store all that back into the place I had just read the memory from. So I'm going to do that long sequence of steps, which I think was like 4 to 5 steps, right? In this one instruction. And that one instruction that does all of that work is only 4 bytes long, compared to this one, which does an extremely straightforward thing that's 10 bytes long. And then another one, which is NOP, or no-op. Funny story, this one originally was defined as it was a instruction that, or I should say it was a byte value that's just undefined. I think they actually did a retroactive, they like retconned it, the retroactive naming of this one. But it's typically the byte 90, or 90 hex, and it's only 1 byte long. So, so basically, that's kind of in a nutshell the lay of the land as far as what you'll have to deal with. This type of stuff, so the kind of explanation I have of what's going on here, what effects it's having in the processor, what sequence of steps it's having to use in order to get from beginning to end, all of those things are part of your job on trying to interpret what algorithm is being implemented by these things. The instruction lengths are things that you're going to have to understand from the perspective of trying to trying to build patterns and signatures and things like that to try and identify segments of code that are in pieces of malware. So you saw some example instructions. Somebody needs to mute. Or I will mute. Let's see. This one. There, I think someone needs, or whoops. Yeah, someone needs to mute their mic if you're connected. There you go. Thank you. If you have any question, or if you had any question, that happens on almost every call that I've ever been on using WebEx at any place that I've had to do calls with. So generalized instruction formats. Instructions can be anywhere from 1 byte to 15 bytes. I really just kind of came up with that looking at all the instructions in a document. I actually found a spreadsheet that had a list of instruction patterns, and I just looked at the longest one. There is no maximum size, as I said earlier. The way the x86 interprets it is that it actually loads kind of the first so many bytes of an instruction in, and then based upon the values there, it actually makes a decision as to whether it's going to read more and read more and read more. So x86 attempts to reserve the shorter instructions for the more frequent ones. So getting back to like this example, one of the reasons why this jump instruction right here is 2 bytes and this move instruction here is 10 bytes is because you're very likely to use this 10-byte variant a lot less frequently than the number of jumps. So a great kind of example of this is if you remember the code diagram that I showed earlier where we implement an algorithm, the form above here, this move Q, effectively this instruction really I think only showed up 3 times, and that's because 2 of them were actually redundant ones where I had intentionally redone the same operation. So really in that code segment, it only happens twice, but if I remember correctly, there was about 4 to 5 jumps in that algorithm. And that's the type of structure you'll see very frequently, which is one of the reasons why the more frequent instructions end up being shorter. So they do kind of strategically work that way. So same, with this stuff. These types of things actually end up being a lot more frequent than some of the other ones that are a little bit more straightforward. So so this is a common layout. This is actually taking these bytes. So like we'll pick on this 10-byte one again. We'll pick on this guy again. The layout in bytes of the instruction is below. So there's typically the first field is the operation, and the second field is what's called the mod r/m. So I'll describe those down there. Let me double check. Okay. Yeah, I have all I just want to make sure I didn't get it cut off. So operations typically 1 or 2 bytes, but it can be 4 bytes. It can be as long as 4 bytes to reflect a kind of modified version of an operation. So a great example of this might be I'm trying to execute a 32-bit variant of an instruction in 64-bit mode. So if you're running in a 64-bit OS on an application that was compiled for 64-bit math, and you, for whatever reason, decide you want to do a kind of modified version, like a 32-bit version of an operation, it'll oftentimes prefix the opcode with another set of bytes. So you can get up to 4 bytes. But that's like literally, a dictionary of values that are mapping to functional operations. so like move, subtract, add, stuff like that. So the next one is this one. I cannot tell you what the abbreviation stands for, but this is the, that's actually a real common term that's used in a lot of manuals. It's a single byte. It tells the CPU how to interpret some of the operands that are to follow. So going back to the previous example, we'll do this again, right? So in this case, this operand is a register instead of memory, for instance, instead of a memory address. This operand is a immediate value. It's an actual number, and you want to use that number as your value. This could easily have also been a memory address, or it could have been another register. And in any one of those cases, there is an encoding. In the case of this operand being swapped for a memory address, in which case I'd want to read 64 bytes out of that memory address and then write them into here, that would still be a numeric value from the processor's perspective. So in order for the processor to distinguish whether this argument, whether that number is supposed to be a value or a memory address that contains a value, that's where this field comes in. So it's basically what variant of the operand am I working on. So the next one is scaled addressing. I don't know what the abbreviation stands for again, but it is dealing with scaled addressing mode. So you can actually have a feature set up so that when you're dealing with indirect addressing similar to this one, that's the third bullet, the add L, you can optionally have a scaling value to that for instance multiplies the add or subtract by like a certain amount of by 4 or 8 or something. That will be very useful if, for instance, you're trying to deal with 32-bit values or something like that, which themselves occupy 4 bytes each. It allows you to step down a array by an increment that's larger than a single byte. So that's why a feature like this exists. So it's called scaled addressing. So again, you can add 2 addresses, and then the indirect mode also allows you to multiply by certain values as well. So the memory indirect operations can actually be very very expressive in a very compact amount of space. And then I have displacement, immediate, etc., and then I have basically ... So this is also how your instructions can start getting out to 8, 10, 12, 15 bytes long, is by having another set of arguments. And that can be, I put a handful of examples up here, displacement, immediate, etc. But they're basically the arguments that you provide. So that's this stuff right here is basically where these arguments start. So I'll get into the registers. As I had mentioned, they actually have a number of what I would call purpose-specific registers. I always like to say it's local memory that's directly addressable by most instructions in the CPU. There's 16 registers total. You'll notice the table has 8. That's because that's the 8 original registers from the architecture. Where the arrow is right now, the R8 through R15, that's actually 8 more registers that if you happen to be writing 64-bit code, you get to use as you wish. And so this is actually something that's somewhat different from other CPU architectures, but it was a very popular design that Intel started with and kept using going forward. They basically define, I would say, roles is a good way to describe it, roles for each one of the registers. You'll notice that they actually have kind of the first 4 of them actually have A through D, but the most amusing piece of it always is that the numeric value and the alphabetic value are not in the same order. So also, if you happen to be interchanging them for whatever reason, or you read any code where they appear to be interchanged, make sure that you're cognizant that R1 does not mean RBX, which is actually R3. So I'll kind of give a little bit of background. The reason for this is that it initially enabled some of the instruction set to be really compact. So it allowed you to make assumptions. As long as certain data was in a register, there are operations that you can actually execute where they just don't need to take registers as arguments. It's just they are hard-coded to work with specific registers to either use the data that's in one of them for their operation or to always store their data in another one. So these rules are not hard and fast. So if you do get down to analyzing instructions, it's always important to read the documentation. And there's a lot of documentation out there, and I think on the previous slide set, on the previous slide set, I actually have that. It has the accumulator is one of these, so frequently that's where result storage is, and that's one of the reasons it's called the accumulator. So it's you perform operations on 2 values, and then the result of that goes into 1. There's a number of instructions that will overwrite the value of the RAX register. So you may want to keep that in mind if you're writing assembly language to make sure that, say, you save the value of that if you need it in the future. So there's a counter. So it's frequently used as I in iterations and loops. So one kind of pattern you'll see where this one gets used a lot is that there are a number of instructions that will automatically subtract 1 from this register when they execute. And then they'll also do a test of this register. So you want to keep that in mind when you're reading code and you see some instructions, especially that have to do with loops and tests and things like that. You want to keep that in mind because that's very likely what they're testing against. And then again, that's one where if you're writing assembly language, you want to beware that the RCX or the CX counter may get modified by some of the looping instructions. The RDX operator, the RDX operand is frequently used as an additional argument in some operations. So one example that I've seen in the past has been that operations that are trying to do work on a value that's larger than can fit in one register will very often assume that the remaining data fits in this register. Likewise, a 3-way operation very often uses this as one of the registers that it's working from. So RBX is called the base register, not to be confused with the base pointer, but it's frequently used as a base address or counter. So this one, very oftentimes you will see in C++ code. And when it's in C++ code, it almost always contains the this pointer. If you're familiar with a this pointer in C++, almost always RBX is occupied by this. So it's a base pointer for a class instance or a structure instance and things like that. So you'll frequently see it uses that. One of the reasons for that is because there are a number of instructions where that whole memory indirect addressing, this thing here, can actually use the EBX register, or I should say can be implied to use the EBX register. It has some hard-coded variants that use less instruction bytes, and then assume that RBX contains the base address for some really complex addressing operation. So our SP is always filled with the stack pointer, and this is one of the registers that generally speaking you don't use for doing any common pointer math or pointer operations in your program. This is one of the instructions that's actually modified by a number of system instructions and a number of control flow instructions. So for instance, when you get to the end of a function and you have a return statement, that return statement typically turns into a return instruction. So there's a one-to-one mapping there usually. I'm simplifying here. When it needs to return, it needs to know where to return to. Typically, that ends up being an address that's stored in what's called the stack, and the RSP, the stack pointer, is the register that's keeping track of that for you. Base pointer, and this one's not part of the internal CPU workings, but there's a convention that uses it a lot to keep track of the base of the CPU stack. So if the CPU stack changes, this helps keep track of where it was at the beginning of a function. And then the final two, there's a source index, which keeps track of indexes of source arrays. So if you remember when we were working with memory arrays and data some of the data structures, stuff like that, the source index very often is used to keep track of the index of the array that's the source of, or I should say the unchanged source of data. And then there's a counterpart to it, which is the destination index. So these, I typically call them the string registers or the streaming registers, because they help you, or I should say the processor has a number of instructions built into it that will assume to be using these two indexes or these two registers for doing iterative string and streaming operations. So that's something that's also important to keep in mind when you're reading through code, is that sometimes you might run into a loop where it looks like an instruction that takes no operands is being executed, and a lot of times that's for these two. Or it's actually getting its input from those two. So you want to look for cases where these two are loaded. I will say that in a lot of cases where you don't do a streaming operation like that, then RSI, RDI, and RBP, all three of those end up being free to use for a lot of other purposes. And so you will also see plenty of general purpose use of them. And technically, as long as you keep track of, as long as you keep track of the data that they need to be when they come into use by the processor, by certain instructions, you can use all of these interchangeably. So they're all directly addressable through instructions. You can overwrite RSP if you want. You may break your program flow unless you restore it later, but you can use any of these 8 as general purpose registers. And then, as I said, on 64-bit architecture, there's actually a number of there's 8 more registers that you can use that actually don't have any defined purpose like this. So you can also use all of them as much as you want. And I don't think that they have fancy names like this either. So you actually would just use this R8 through R15 naming. And as I had mentioned earlier in the examples, it's usually something like this. So you can see I have RBX there. You could actually do like R12 to work with it. So then we'll get the memory addressing discussion. So instructions, they can have varying addressing modes that represent common programming patterns. So the entire reason these complex things exist is because computers are around so they can do really complex data management, data manipulation, data interpretation, however you want to explain it, operations. And those of you who had to deal with like any kind of signal processing and stuff like that, probably familiar with MATLAB and the whole like matrix matrix calculations and stuff like that. A lot of those use cases is the reason why many of these things were put together, because a lot of these processors existed, or I should say were created for the purpose of solving those problems very quickly, so that people wouldn't have to do them by hand or with a slide rule or whatever. So below I list the addressing modes that that are available for the instructions. So these influence this right here, and then these things over here. So what arguments are provided. So the you know, the most straightforward one, or the simplest one, I would say, and the one that typically results in the most compact instructions, is register addressing. And because of that, that means that a lot of times when you are dealing with, or I should say, when you write C code or C++ code and you are dealing with I wish there's
figure out who
it's nobody's
doing
fault.
that?
It's nobody's fault. It's a because I can see the thing right here.
There's gotta be something.
Yeah, the problem is that there is an electrical connection that is broken somewhere. And they keep coming out here to try and figure that out, but they can't reproduce that.
I have a class like literally 2 hours before this where they use the same stuff and it doesn't happen.
Yeah,
I feel like
because they don't run, they don't ever turn that on from the computer. So I'm actually going over here to try and see if I can, just mute the speakers and see if that helps. Because this thing didn't mute. So we'll see if that works. So back to this.
Sorry.
It's okay. So there's immediate, I talked about the register addressing. That is basically having the instruction operate on whatever CPU registers, the things that I listed up here. Then there is immediate addressing, which is located right here. And this one allows you to directly express values, so numeric values, in the instruction. So for instance, I have, in this case, I have the value 10 or the value A hex. I want that value put into the register RBX and overwrite whatever else used to be there. So let's see. Just give me 1 second. Okay. I just want to check something. Okay. So then the other one is direct memory. And this is the one that's kind of interesting because normally you would read this. This is where it's very important to know that there's these different ways of expressing it and how they're actually expressed. Just reading this one, you know, yourself, you would think that it's trying to put this value into RAX. This is actually telling it to, I'm hard coding the address in the instruction of 1000, which is usually 1000 offset, or that's 4096 in decimal. It's trying to, it wants you to go to the memory location 4096. It's actually the offset from a base that's your data segment. And then store the 64-bit value you find there in the RAX register. So these two in source code, in assembly language source code, look like they do the opposite thing that they really do. When you first look at them, they look like they do the opposite of the intuitive interpretation. So just keep that in mind. So then there's this other one, which is called register indirect memory. And in this case, RBX contains a number, contains a value. That value is supposed to be interpreted as an address. So rather than copying the value in RBX and putting it in RAX, it says, get the value at RBX, pretend that it is a memory address, pull 64 bits out of that memory address, and then put them in RAX. And you differentiate this one, so number 4, from number 1 using parentheses. Again, I'm using the AT&T syntax here. So to make things even more complicated, the Intel syntax looks almost completely different from this.
Explain that again.
I really don't know. I have it muted. I have that thing muted, or I have it muted there, I have it muted here. So I don't know what the problem is. But it always does that like later on in class too. I'm gonna probably have to open another complaint about it. So we'll try and see if we can get through this without doing that again. So it was the register indirect. Register indirect plus offset. So again, this is one where the intuitive visual interpretation of this might defy you, so you want to be aware of that. In this case, your first assumption when you see this on a line is to think that, okay, we're multiplying 8 by the value that's in RBX, but that would be an incorrect read of this. This is actually telling you to add 8 to this register's value to get the address that you're then going to read data from, and then put that data in RAX. But then you'll remember that I did mention that there is a scaling value that you can use as well, and that's this next one, the second from the bottom. So the second from the bottom says that I want to use RBX as my base, and then I want to take, let me just try this. Yeah, and then I want to add 8 to it. Or no, I want to take RBX as my base. I want to multiply 4 by it, which is C here. So I'm going to multiply 4 by the register's value before I then add 8 to it.
And that's an address.
And that's an address. Before I then go and fetch the data that I want to put in RAX. And then finally, there's the last one, which is I store my register in a base, which is this one, RDX. And that's the reason why this first argument is actually vacant, is that there is no base. But I store the register in a base. I take this register, RBX, and I multiply it by C, which is 4, my scaling factor. And then I add that, and then I add that to the base, and then I also add 8 to that. So that whole expression there is also supported by the instruction set. And the historic reason behind a lot of these is to go back to dealing with large matrices, multi-dimensional arrays, and things like that. This ends up being a very handy way of like dealing with data where there's a large data array, but there might also be some lead-in header information and things like that. This gives you the ability to have those blocks arbitrarily in memory and more or less keep like this offset the same to make sure that you align yourself right when you're trying to do a scanning operation. So that's the end of the memory addressing, and the next class we'll get back into dealing with Yara, but we will deal with it for the application of trying to match on this, or trying to turn code with this type of stuff into Yara signatures. So, and we have about 5 minutes left, so I will go ahead and end class right now rather than trying to jump into a demo.
Is there any updates about what we should expect for the next homework assignment, or?
So I was gonna try and have it this week, but probably Tuesday's more likely now.
Tuesday?
So
Okay.
yeah, so next homework is probably more likely to be Tuesday.
Professor, you don't have a lot of time. On
Yeah.
Thursdays was just a few questions. If you can give
Sure.
short answers.
Yeah,
just
I
first.
mean, I ended, or I should say I.
First few are related to the homework. I finished all the attack. I performed them, everything. It's just that for I just need to understand for the PDF attack, the Accumulator, when I generated or when the Metasploit generated the PDF file,
Yeah.
and then I moved it into the Windows machine.
Yeah.
Double-click it,
Yeah.
open in the Acrobat. It actually generated a second PDF file.
Mm-hmm. Yeah.
And it asked me to save it. Is that
Yeah.
normal?
Yeah.
So
So pretend that you're a user who would click yes to
the
that.
exploit that I have used is
Yeah.
the embedded EXE.
Yep.
Yeah.
Yeah, so just pretend that when you're trying to run it on there, pretend you're a gullible user and click yes to the
Yeah,
prompt. So
yeah.
yes, I do want to run it.
Yeah.
So yeah, feel free to do that. And then also make sure that you just kind of include that observation in your report. And then you could even comment on.
This is first one. Second
Yeah.
one is when I started the homework, one of the first requirement is to establish a connection between virtual machines and
Yeah.
to actually validate that the TCP can
Yeah.
packets can pass between the
Yeah.
virtual machine. I was not familiar at that point with the netcat.
Okay.
So I wrote a small piece of code
Yeah.
using Java, and I installed Java runtime environment.
Yeah.
And it did that. Later on,
That's fine.
when I went into moving file between the virtual machine, I did not want to first use the connection between the virtual machine into the host.
Yeah.
Then going back to the guest because I don't want any malware.
That's fine.
So I used Netcat to transfer the file.
Perfect.
And with Netcat,
Yeah.
Wireshark actually captured TCP.
Yeah.
So if I included the image,
Yeah,
both
yeah.
images in the report. If Java code you don't like.
Java code's fine.
Yeah.
Yeah.
Okay. So yeah,
I can read anything.
Okay. Final thing related to the homework. Do you prefer PDF or Word?
Either one, just make sure that you upload it.
Yeah, and directly.
yeah. Yeah,
Word. Okay.
and what I usually end up doing is I'll upload multiple files. I'll upload a zip file and also the Word document.
Yeah,
to
I
the
have
assignment.
saved the try before.
Yeah.
Before coming here with both Word and PDF.
Yeah.
Few questions related to the assembly.
Sure.
This lecture. First question is since the C++ compiler actually translate the code into machine instruction or binary code, right? Not like let's say C# or VB.NET, in which they do some sort of a pseudo code
So what?
intermediate.
So
Why do we have different compilers for different OS? I have same machine running
Same
multiple,
hardware.
If
Yeah.
I compile for the Windows, is it supposed to be when I use C++ which compile to a binary code? Shouldn't it also run on the same machine because the architecture of the CPU is the same?
Yeah. So the difference is that the instructions just implement very micro operations. So very micro operations for algorithms within the system. However,
The only thing that's actually
Yeah, that makes
true
sense.
is this.
your program still needs to assume that that certain data is in memory and stuff like that, and that the interface to call functions and everything is the same. Like all of that stuff's not hard coded in the architecture. Those types of things are OS level differences. So for instance, if I have a function call,
Yep.
there's an instruction
I'm not even
in assembly, there's an instruction
I haven't-
that's
I
called
haven't
call.
included my screenshots for any
That
of the
instruction
videos.
doesn't take any arguments other than the address of the function.
So I've got like
So
5 more screenshots
the way
of
that
screenshots
arguments
for
get to a
Flash
function call
than I have
is
for the other
different
apps.
from
And
OS
I'm
to
gonna have
OS.
do
Oh,
all my
I see.
files.
And so one of the things that the compiler does, in addition to just translating your C++ code into assembly, is it also decides what sequences of instructions accomplish what macro operations in C++ you're trying to do, and that is actually different depending on operating system, even though they use the same CPU under the hood.
Second question is, during my undergraduate, I was messing around with the reverse engineering stuff, and I tried to actually figure out a way to decompile from binary data file in binary exe file like an
Yeah.
application, and then translate it into assembly code. But I have faced a problem in which is it easy if, let's say, I contacted Intel, or is it easy to get the table of instruction of, like, let's say,
Yeah.
or
So I
is
think
it available on the net, or
I think the let me see. I think I have.
Most standard sets are
Yep.
available, and then if it's a specialized instruction set for specialized hardware, depending on the company, you can actually email them and ask
Yep.
for their instruction set, and most places will do it.
Yeah, so I'm trying to see. Yeah, I actually have like this right here. This is on the lecture notes, the 5-2 lecture notes. So I just posted the announcement in Blackboard today that has a link, the direct link to all these slide decks. This is, I think, on the I can't remember which slide, but it's like number 7 or something. So this is a site that someone has been putting together, like not Intel, not AMD. AMD actually publishes the PDF for all of their manuals. Intel also does the same thing, and I
just loaded over a Hello World script.
can't remember how long ago I did it. It was like 10 years ago or something. I actually emailed AMD and then asked them to send me. Asked if they still. I actually said I asked them if they still shipped the published documents, and then they sent me a response back by email that said, "What's your address?" And then I gave them my address, and they sent me a box with all the things, and they paid shipping and everything like that. So a lot of the processor vendors, including the big ones like Intel and AMD, more than happy to a lot of times supply those things. They might not publish them as much anymore because PDFs are so easy now. But back like 10 years ago or whatever, a really, really large PDF was considered to be a bit unwieldy, and a book is nice because you can like highlight things. But for most of the, and if you're dealing with any processor, like any of the embedded ARM processors or any application-specific processor, almost all the time if you contact the manufacturer, they're more than happy to supply you with tech docs because they would really like you to use it for whatever project you're trying to do instead of going to someone else who will give you the tech docs.
Okay, so last question.
Sure.
Really quick. From previous knowledge, I know that when the exe is like the instruction stored on the hard disk, right?
Yeah.
There are like the addresses of the memory are relative to the entry point, something like that. And when the exe is loaded into the memory, it's actually translated into absolute. Can we
Remember if I have that in here.
can we use something like a hint from the if the program is using a relative or absolute to detect that a program might be a malware?
You can't use the
Like it's trying to access
Yeah.
something.
So the first one is the program will have a base address. So the program will have a base address. That's the address that most of the memory addresses are defined to operate from. The program will also have a separate entry point address that is
or the first
offset.
instruction.
Yeah, that's offset from the base address. You might be able to use the value of the base address as an identifier of some malware,
If
but
the-
I don't know
yeah.
what rule that would require doing the analysis to get a bunch of malware, get a bunch of legit EXEs,
Yeah.
and then try and see if there's a signal out of that somewhere. So trying to do some, really kind of simple static analysis across all of them. So we'll actually probably jump into some approaches I use for like bulk analysis or mass kind of cross analysis with things like that a little bit later. That'll probably be after we get through some of this Yara analysis. Because a lot of times what I'll end up doing is I'll like pull I have a directory of 1,000 malware samples, right? If I have that, I can't very well open every single one of them.
Yeah.
But I can run the OBJ dump tool across all of them, right? And then I can pull out the base address. So a lot of times what I may end up doing is I may end up importing that data into like Mongo or SQL database or something like that, where then I can do more kind of complex bulk operations, like show me all the malware samples that have this base address. Show me all the base addresses that have the highest 5, occurrences in my malware set. Like those types of analysis I'm capable of doing once I load it into an SQL table or something. So, yeah.
Thank you.
Yep.
Go ahead. I sent you an email to follow up on what we talked about last week.
Yeah, I got it. I forwarded it to my,
Okay, awesome. I just wanted to check and make sure I sent that to the right place.
Yeah.
And then, so just kind of a flavor difference between Intel and what we were looking at, the AT&T stuff.
Yeah.
So I know Intel uses. Why does necessarily Intel specify that you're using like a D word pointer or a Q word pointer? Because those are the equivalent of the parentheses, correct?
The pointer is.
Yeah.
Yeah.
So like if you're calling D
so-
word pointer REX or something,
Yep.
you know?
So
Brackets,
they,
REX, I think it is.
so if you remember, let me see if I can go back a little bit, I'll show you. So that's telling you what the data is supposed to be
Yeah.
at that location. So that's allowing you to, I'll go this way.
Yeah.
Let me
Sure.
see.
Or would it be?
That's
Is it,
allowing
it's just
you
a
to
simple move
choose-
instead of a move quad.
Yeah, well,
Okay.
it's because Intel never uses
Yeah.
this suffix.
Okay. That's what I
It's
thought.
telling you whether it's, so D word would be L,
Yeah.
and then
D-
Q
D
word would be
is
Q.
quad. Yeah.
Yeah, and so that's basically the way
Okay.
on
Yeah,
Intel
that's what
syntax
it
to
is.
express that.
Okay.
AT&T syntax expresses it that
Mhm.
way.
Okay.
And then the operands are flipped, which is the other one.
Honestly, I've never realized. Well, I kind of have realized it, but I've
Yeah.
never like strictly thought about it because of how often I have to go between the two. Because just the tools and stuff I use, I'm
Oh, okay.
so used to like flipping everything around that I'm like, hold
Yeah.
on, what language am I looking at right now? So
Yeah, I
so
end
I'm
up
always
dealing
like,
with
okay,
that
this
too.
is moving this and yeah. So I was just like, wait, why is this one using keyword pointer? And I
Yeah.
don't know.
But
It's
that's
just,
literally the way
yeah.
that you
Mhm.
accomplish the suffix in AT&T on the
Okay.
Intel side.
yeah. So it's pretty much the same.